When you think about it, from the smartphone that's probably in your hand right now to the spacecraft orbiting way above our heads, the quality of the products we rely on isn't some happy accident. Nope, it's engineered with this incredible, almost invisible precision. Today, we're going to pull back that curtain and look at the amazing tech that makes it all possible. So, how are we going to tackle this? Well, we've broken it down into 5 key parts. I want you to think of this as your personal cheat sheet, the essential lecture notes on the tech that honestly makes sure our world works the way it's supposed to. All right, first up, let's set the stage. We need to understand why this whole thing is so absolutely critical in any modern industry. And believe me, it's about way more than just making sure things don't break. At its very core, quality assurance, or QA as you'll hear it called, is about building a stable and consistent foundation for everything that comes next. It's about systematically wiping out human error, making sure you're meeting all those strict regulations, and at the end of the day, guaranteeing that the products you use are both safe and reliable. And here's the crucial point, the real takeaway. Modern QA isn't just about playing goalie and catching errors after they've already happened. Not anymore. It's about building these smart systems that actually prevent mistakes from ever happening in the first place. It's a huge shift from being reactive to being proactive. So if the goal is to stop mistakes before they even start, how does the system know what to look for? Well, it all begins with data. And to get that data, you need an unbelievably advanced digital eye that can see things that we just can't. This right here is the front line of modern defect detection. Machine vision systems are doing jobs that are either completely mind-numbing or just physically impossible for a person to do. And they do it thousands of times a minute without ever getting tired or needing a coffee break. And the range of what this eye can do is just incredible. I mean, on one hand, it's doing something as simple as sorting parts by color at lightning speed. But on the other, it's using these crazy techniques like digital image correlation to literally watch how metal stretches and deforms under stress, hunting for tiny microscopic weaknesses that could lead to a total failure. It really sees everything. And look, this isn't just some theory. The results in the real world are stunning. One system mentioned in our sources could identify and sort wooden blocks by color with a 97% accuracy rate. Can you even imagine a person trying to do that for hours on end without their eyes glazing over and making mistakes? No way. Okay, so having a digital eye is one thing. That's a huge step. But making sense of all that visual data in real time requires a powerful, intelligent brain. This is the real game changer. This is where the process goes from just being automated to being truly intelligent. See, the AI doesn't just flag a problem and say, hey, this one's bad. It figures out why the defect happened, and then it feeds that info back to the production line. It's basically teaching the other machines how to not make that same mistake ever again. It is a cycle of constant automated improvement. And it all comes down to this simple 3-step process: detect, analyze, and improve. That's it. That's the engine driving modern quality control. It's a continuous loop that just gets smarter and more efficient with every single part it looks at. And the results? Well, they pretty much speak for themselves. In one case study we looked at, putting this kind of automated feedback platform into a production process pushed the overall pass rate, that's the percentage of perfectly made products, to over 90%. That is a massive, massive leap in both efficiency and quality. Okay, so our system can see defects and it can think for itself. But how do we actually prove that a part meets specs that might be measured in nanometers? That's billionths of a meter. That's where the science of measurement comes in. Metrology is kind of the unsung hero of the entire quality assurance world. It's the science that guarantees a millimeter in a factory in Germany is the exact same millimeter in a factory in Japan. Without that level of precision, global manufacturing would just fall apart. And the toolkit for this is just, wow, it's so diverse. You've got tools that let us use X-rays to peer inside a finished part to find hidden flaws. We can analyze a surface at a microscopic level. We can even measure tiny, imperceptible vibrations that could throw the whole process off. It's like a multi-sensory approach to proving perfection. You know, this quote from the research just sums it up perfectly. It's so simple. You can't control what you can't measure. All the incredible progress we've seen in the quality of the things we buy is built on the foundation of being able to measure things with more and more and more accuracy. All right, we've seen how all the components work. We've got the eyes, the brain, and the ruler. So let's wrap this up by looking at the bigger picture,
and what's coming next. And with all this incredible technology we've just talked about, it's a totally fair question to ask, right? Have we finally perfected manufacturing?
The answer, and this probably won't surprise you, is not quite. It seems like for every problem automation solves, human innovation creates a new one. As we move into really advanced methods like 3D printing, we face totally new challenges. Things like microscopic gas bubbles trapped inside a metal part, or hidden electronic faults on a circuit board that are totally invisible to the naked eye. The race for perfection, it turns out, is never really over. And this brings us to the ultimate vision, the final goal for the future of quality. It's not about just building better inspection tools anymore. It's about creating these fully integrated, self-correcting systems that are so smart and so adaptive that they achieve perfection by design. The goal isn't just to find the needle in the haystack anymore. It's to engineer a process that builds a haystack with no needles in it in the first place.